Before you look at the answers, score yourself honestly and email me your score before Monday night once you've taken it. What I did wrong, or maybe how my answer is the same as what they say is the answer, I will give you extra credit. Here's an expression for the kinetic energy of the bullet, and that's going to be part of our final answer. We need our final answer to be some multiple of this, of 1/2 m1v1 squared. So 1 subscripts are going to mean bullet, and 2 subscripts are going to mean gun. Here's my momentum conservation analysis. The system starts with a momentum of 0 before the gun is fired, and then the bullet moves with a forward momentum, and the gun will have a backwards momentum that are equal in magnitude but opposite in direction. Solve this expression for the final velocity of the gun, and we end up with negative m1v1 over m2. Plug that into the kinetic energy formula for the gun as velocity 2, or velocity of the gun. Square everything. I'm just going to square it before I do any canceling. And I'm going to now cancel an m2 over an m2. We'll still have one m2 remaining in the denominator, and I'm also going to move this 2 into the denominator. What we're going to now do is try to figure out how does this relate to the kinetic energy of the bullet, which was this first expression. I'll put it here again so we can refer to it. This expression is some multiple times this expression. So all we need to do is just factor out the kinetic energy of the bullet. And there it is. What's left over? m1 over m2. And so to me it seems like the answer should be m1 over m2 times the kinetic energy of the bullet. That is not an answer choice. So once again, the first person to email me and tell me either what I did wrong or why maybe my answer is the same as the answer that they say is correct, I will give you extra credit. The answer that they say is correct, incidentally, is D. Alright, so here we have a pretty straightforward center of mass question. If you don't remember the formula for center of mass, you can go look in your notes or your textbook or in lecture 9.8 on the YouTube channel, which is about motion of a system of particles. But instead, I'm going to show you that we don't need the formula. We can just do this sort of logically. I'm going to just draw an arbitrary 2 lines and show the geometric center of this almost square shape. And what I want to determine is, with respect to the intersection of these lines, this sort of fake center, this is not the center of mass, obviously, but this is just like the center I chose. With respect to this spot, 1, 1 would be its coordinates. Is the x center of mass to the right or to the left? And is the y center of mass above or below? Starting from the x center of mass. Well, because of this extra piece of wire up here at the top, there's more mass to the right of x equals 1 than there is to the left of x equals 1. So your answer must have a greater than 1 x value. All right. Same thing in the y dimension. Starting from the center, again, this spot that I drew, these intersections, this intersection, there is more mass below because there's sort of a missing piece of wire here, and it is not missing at the bottom. There's more wire below than there is above it, and therefore the y center of mass must be something less than 1. And the only answer choice that has a greater than 1 x value and a less than 1 y value. Really straightforward projectile motion. The only slight trick to it is that 30-degree angle. So let's see if we can account for that. All right, in this question, I want to make special mention of something that we talked about many, many times, and some of us are still making an error with, and it's this. The 200 will not be used in my math. I will never, ever plug in the number 200 into kinematics. The reason is that that number is a velocity in 2 dimensions. We can therefore break it up into an x and a y component using SOHCAHTOA. And when we go to do kinematics, you can only ever use values that are in a single dimension. Now, that said, I'm only going to choose to use the y dimension because I know the acceleration in the y dimension. I'm going to put a subscript of y in this acceleration. And it's the acceleration due to gravity. So let's first figure out some stuff that's implicitly understood about anything when it reaches the apex of its trajectory. It will still have the same horizontal velocity, this number 200 cosine 30, which is about 187 or so. And that's because there are no forces acting in the x dimension. There's nothing to change its velocity, and so it has this horizontal inertia that keeps its horizontal velocity the same at all times. Its vertical velocity is constantly decreasing. It doesn't mean it's always slowing down, it just means it's always becoming more negative. So, for instance, when it's moving upwards, it's slowing down because the acceleration of gravity is slowing it down, and then as it begins descending, it is speeding up, but still becoming more negative, so therefore decreasing. Anyway, velocity in the y dimension is 200 times the sine of 30, and if you do the math, sine of 30 is 1/2, so this ends up giving us a vertical component of velocity of 100 meters per second, and that literally means that at the instant this thing is launched, it is moving up at 100 meters per second. Its total speed is 200, right? We already knew that, but how fast is it moving in just this dimension? 100. So that number is going to go in here, and for Vy, this will mean at the apex, or the highest point in its path, and for any projectile, the y velocity only, vertical velocity only, is instantaneously 0 at the highest point in the path. So plugging in the numbers we know, squaring my 200 sine 30, and then solving it for delta y. Okay, this question is going to force us to do a little bit of calculus. Equation A is equal to 12t. You can get a velocity function by integrating an acceleration function with respect to time. So the integral of a dt, starting from 12t, so this is just reverse power rule. Oh, I didn't do that. Oh, whatever, who cares. So this was like 12t to the first power. So when you want to integrate something with power rule, you just raise the power by 1, and then you divide the entire expression by the new power. So t to the 1 becomes t squared, and then you divide everything by the new exponent of 2, so 12 over 2t squared is the integral with respect to time of acceleration, and therefore 12 over 2 simplifies, you get 6t squared. And then there's always this plus c whenever you do an integral, because there could have been some constant there, which, when you take the derivative would have gone away. We have actual physical meaning for that. It's the initial velocity in this case, but we know that to be 0 from the prompt, so I'm going to get rid of it. We can now go from velocity to position function by integrating the velocity function with respect to time, so the same rules are going to apply. This 2 is going to be raised to a power of 3, and then the entire expression will be divided by that new exponent of 3, giving us 2t cubed. And again, plus c, or the constant that could have been there, would mean, in this case, initial position, but we also know that that's 0 from the prompt. We just need to evaluate this now at time t equals 2 seconds. Doing that gives us 16 meters. Question 13 is actually something out of our last unit, which we will begin the week after next. So don't feel bad if you didn't know how to do it, but as you probably already figured out, this is a full-length AP test, and so I wanted you to try these questions because inevitably you're going to see some questions on the real test that you won't know how to do. Maybe you've gotten pretty good at guessing, so let's see if you got it right anyway. First thing to consider is you have three answer choices that talk about simple harmonic motion. We don't know what that is, but I'm just going to tell you, and then what I'd like you to do is pause the video after I show you this and see if you can then answer the question. Alright, so the force for anything that moves in simple harmonic motion is equal to negative kx. This means, and this is like the defining characteristic of what simple harmonic motion is. That means that whichever direction something moves in simple harmonic motion, the force acting on it is in the opposite direction, and it changes proportionately with the force. So this should be pretty familiar to us. We've seen this formula, right? This is Hooke's law. And that means springs are one really common example of objects that move in simple harmonic motion. If you like attach a block to a spring and then pull and let go, it'll sort of bob back and forth in such a way that the force the spring exerts, F, is always proportional to the displacement. So if you pull a spring, the spring pulls back. If you pull the spring farther, the spring pulls harder. That's kind of what this says. So now you know what simple harmonic motion is. I'd like you to do, pause the video and see if you can figure out which answer choice is correct. Alright, so we said a moment ago that simple harmonic motion is characterized by Hooke's law, or something like Hooke's law anyway, where the force and the displacement are proportional but negatives of each other. That is not the case here. It's not the case here, and the reason is that this ball is being acted upon by gravitational force, which is always the same amount and in the same direction. It's down, and it's equal to mg. Therefore, it doesn't change as a function of displacement, nor is it always the negative direction of the displacement. So we can already discard answer choices A, B, and C because of the gravitational force not being negative and proportional to displacement. E talks about constant momentum. I think that's clearly illogical, right? This ball is going to speed up and slow down constantly, and so its momentum will always be changing. And that leaves D. D is the correct answer here. And the part about the period being 2.8 seconds, not really that crucial that you know how that was done, but if you do care, you just do a little bit of kinematics and you figure. Video number 14. Here we're looking at an object that moves in a straight line, so we can restrict our analysis to one-dimensional motion. It has some velocity that changes as a function of time. So the function is 4 plus 1/2 t squared, and we want to know the acceleration at the instant t equals 2 seconds. This could not possibly be a more straightforward question. This is the easiest question on the test, probably, if you know how to do it anyway. So all we're really looking for here is a way to go from a velocity function to an acceleration function that we can then evaluate at time 2 seconds. Well, what's the relationship between them? A, or acceleration, is the time derivative of velocity. So we could express that as A equals, there's sort of different ways you could say this. You could say sort of V prime, and the way I like to do it, you've seen me do this more often, is the instantaneous change in velocity over the instantaneous change in time, dv dt. That's how we often say that. Okay, so how do we take a derivative for this type of function? Power rule, that's all this is. Remember that anything that's a constant has a derivative of 0, so that's going to be nothing. And so the acceleration function will be A is equal to 0, which I'm not going to write again, plus, now what's the derivative of 1/2 t squared? Well, whenever you do power rule, you take the exponent and you multiply it by the coefficient that's already out front. So 2 times 1/2 is 1. And then you lower the exponent by one integer value. So 2 becomes t to the first power, which is just t. I'm not going to write the first power there. Now I want to evaluate this at time 2 seconds. So what do? I plug in 2 for t, and then therefore A equals 1 times 2, or A is equal to 2.